Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a video in a series on optimization problems for differential calculus. In this specific video, I'm not going to do calculus because I really despise that some authors put these styles of problems in a calculus textbook when you don't need calculus to solve these. I teach my intermediate algebra students to optimize these problems. So I want to show you how to optimize these not using calculus because it's pointless to use calculus. It's like using a sledgehammer to put a thumbtack in a wall. There's no point to use such a heavy tool for that. Same thing here. So let's talk about this. A baseball team plays in a stadium that holds 70,000 spectators. With the ticket price at $11, the average attendance has been 28,000. Obviously, they would like to draw more people in, so they drop the price to $10. They drop it by $1. By the way, I could tell this problem was written a very long time ago. Anyway, they dropped the price by $1, so now it's $10, and the average attendance rose to 35,000. What is the optimal price point to maximize the revenue? Maximizing revenue, maximizing profit, minimizing costs, all these can be done without calculus. Specifically when somebody hands you a problem where they say, hey, you know what? I noticed that this many widgets were sold at this price, but when we raised or lowered the price by a certain amount, we had this many more sell, or this amount fewer sold, or something like that. So this I want to show you how to do using good old algebra. And I use an online homework system, and the problems in the online homework system are often coded by mathematicians. And what I notice is the vast majority of optimization problems that have been coded are these styles for calculus. And it chaps my hide when I see that, because I think, man, you don't need calculus for this. Stop having students use calculus when they don't need to. All you really truthfully need to remember, and this is whether you're using calculus or not, is that revenue is cost times number of units sold, or price times number of units sold. So price times units sold. That's what your revenue is. That's not actually your profit, by the way. Your profit is revenue minus cost. So that's why I didn't word this problem with the word profit, because that would be incorrect. So let's go ahead and take a look at their base revenue. So initial revenue, revenue sub I, we'll call it. Well, they were selling tickets at $11, and when they did that, 28,000 people showed up. That's kind of nice, right? So you could compute that out if you want to. It's $308,000. That's not actually part of the problem, but I kind of like the perspective when we see that. So it's 308,000, and that's in dollars, because it's $11 per ticket, and so the units on this would be dollars per ticket, and there were 28,000 tickets sold. So the words tickets cancel, and you just have the units dollars. Anyhow, all right, so that's the initial revenue, but we find out that when we drop the price to $10, the average attendance rose to 35,000. Now, so that's revenue after the price increase. So let's just say revenue sub P for after a price increase or decrease, sorry. That's 10 times 35,000. Neither of these numbers, by the way, that I'm writing here need to actually be computed to do this problem. I'm just showcasing the mindset here. So $350,000 is what they get when they drop the price, because they attract more people. And this gets you thinking, hey, you know what? We might be able to earn more money by dropping the price further. So let's create a revenue function. Remember, the revenue function is price times units sold Now just think algebra, not calculus. If you let X equal the number of price drops, number of $1 drops, I guess, right? No, we'll do of price drops. Okay. So let's see what happens here. A revenue is equal to, well, the initial price was $11 a ticket, right? But we're going to do a bunch of price drops. And each price drop will drop the price by $1. That's what we're doing. So we're going to have a $1 price drop for each price drop. So if we have 5 price drops, the new price will be 11 minus $1 times 5 of those price drops, or $6 a ticket. And you don't have to do a price drop of $1. If you want to do price drops in steps of $2 at a time, you could totally do that. But the information they gave us was based on a $1 price drop, so we're going to stick with that. Well, the number of attendees that we get, well, we originally had 28,000 attendees. So that's what our original number was. And we gain how many? Well, we gained 7,000 attendees. So let me just note that this is an additional 7,000 attendees when we dropped the price by $1. So we can assume that the price will, for every $1 that we drop the price, it's kind of a tough assumption, but we can try to assume every $1 that we drop the price, it creates 7,000 more tickets sold. So we'll add 7,000 seats filled in the stadium per price drop. So if we had 2 price drops, we'd add 2 times 7,000, or 14,000 people. If you take a look at this function, so this is now the algebra that I teach my algebra students. If you take a look at this function, this is a quadratic function. If you multiply through, which I highly recommend you don't, if you multiply through, you would get a negative 7,000x squared plus some stuff, right? So it is definitely a quadratic. And if I wanted to graph this quadratic, I could find the x-intercepts very easily, I suppose. Let me drag my ruler down here just to create an x-axis. And now I don't need the x-axis anymore, so I'll turn off that ruler. And if you set the function equal to 0 and solve, you'll get the x-intercepts, right? And so the x-intercepts here, whoops, that's supposed to be 28,000 minus 7,000, plus 7,000 x. The x-intercepts occur at 11, and at 28,000 divided by, or negative 28,000, I guess, divided by 7,000, which is a negative 4. So I'm going to plot a point at x equals negative 4, and I'll plot a point at x equals positive 11. Remember, this is a parabola when you graph out a quadratic. All parabolas look, especially when they're upside down parabolas, which this one will be, look like this. I mean, they go on forever down below, but we're doing a realistic problem here. So halfway between these x-intercepts will be the vertex, or the optimal number of price increases. That point right there is halfway between 11 and negative 4. Halfway between means the average of. So the x vertex for the x value for the vertex, I should say, x value for the vertex is going to be the average of 11 and a negative 4. And what is that? 7 halves? So 3.5 or 7 halves. You could write 7 halves in there. That's totally fine. So I know the x value for the vertex is 3.5, which tells us that our revenue, because this is the revenue function, our revenue is maximized when we have 3.5 increases of, or decreases of $1. That's when our revenue is maximized. So what is the optimal price point? 3.5 price drops. So let me go ahead and say that. 3.5 price drops. But each price drop is $1. That is, if we originally charged $11, we want to drop the price by $3.50 to $7.50. All right. And just double checking my math. Yep, that is correct. So $7.50 would be the optimal price. Notice I didn't use calculus here. You could totally check what the actual new revenue is. The revenue at 3.5 price drops is going to be $7.50 per ticket times 28,000 plus 7,000 times the 3.5 price drops. And so I'll pause and compute that. And that comes out to be $393,750. And in comparison, just to let you know, the original amount of revenue was almost $90,000 less than that at the original ticket price. And when they dropped the price by $1, that's still $43,000 less than the optimal revenue. So this is a great use of algebra, not calculus, algebra. And when you see a problem like this in a calculus class, I would still do algebra because it's just clean, easy, and it's great to use algebra over calculus. Remember, my advice is always algebra before calculus. Actually, it's arithmetic before algebra, algebra before trig, trig before precalculus, and precalculus before calculus. The last thing you should do is calculus.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.